All right, class, we're going to take a look at your review here. See what we can do with this quickly. First question here asks us to determine the velocity of the object. So we'll write down our equation for our average velocity. Average velocity is change in position over change in time. No trouble here. Okay, so here's our average velocity. I'll put a little average down at the bottom. Change position over change in time. And the change in position is the rise on the graph, which would be y2 minus y1. 60 is y2, 10 is y1, and the difference would be 50. The run on the graph would be from 0 seconds out to 6 seconds. So 6 minus 0 would be 6. So we divide here. Again, we get 50 meters divided by the 6 seconds, and that will give you 8.33 meters per second, I believe. Now it wants to write a mathematical equation to describe the motion of the object. And this is a very important phrase right here. And that phrase will definitely occur once or more than once in the test. And all it wants us to do is it wants us to write y equals mx plus b for the line on the graph. And we've done this before in class for the lab. So I will write down x in meters is equal to, notice that is on the y-axis, so I put it where the y stuff goes in the equation, to the left of the equal sign. And I'll even move it over a little bit. Maybe I won't move it. Oh, there we go. I'll move it over so it'll slide up and line up into the y there. And the m is the slope, that's the velocity, 8.33 meters per second. So here I will write 8.33 meters per second. On the x-axis, I have time in seconds right here. Okay, plus my y-intercept, which is 10 meters. That's the b in the equation. So 10 meters. That's it. Done. Okay, next question. Now here at right is going to be a velocity graph. Pop to a new screen. Okay. So we'll look at the velocity versus time graph, and we have 3 different velocities that are constant velocities. For the first 2 seconds, it's going to go 4 meters per second up here. And then for the next 2 seconds, it'll go at -3. There's no -3 written here, but it's between -2 and -4. It's -3. And then the next 3 seconds, it'll be stopped. Like I said, 2 seconds going at -3. It's only 1 second there. So it asked me to describe the motion of the object. So I would say, okay, moves in a, I'm going to abbreviate positive with a positive sign, moves in a positive direction. At 4 meters per second for 2 seconds, comma, look at the word then in a negative direction, I'll read with the word negative with a negative sign, negative direction at 3 meters per second. And I'm not going to put a negative redundantly in front of the -3 because I already said negative direction. I don't need to state the direction twice with a minus in front of the 3 and a minus out here for 1 second. Okay, and then it stops. Okay. Draw the corresponding position versus time graph down below here. We'll do that next. And then how far did the object travel in 1 to 2 seconds? There's more than one way to say how it traveled. I'm going to first use the velocity versus time graph here. So here is 1 second and here is 2 seconds. And how far it traveled is the area under the velocity versus time graph. So this shows me the displacement, or the change in position. And to find that area, I would multiply the height, 4 meters per second, times the base. The base would be 2 minus 1. Or I could just put a 1 if I wanted to. I'll be a little detailed here. Put 2 minus 1, which is 1. And I get 4 meters. All right. Let's go ahead and take a look down below at the graph. And we will see what we have to do down on this graph down below. All right, the first thing it wants us to do is draw the position versus time graph. And so it doesn't really matter where we start, and that is because the graph above tells us initial velocity is 4. It doesn't tell where we start, though. And so I'm going to go ahead and start at the origin. I will draw a slope with a line that I'm just going to say that's a slope of 4. Okay, I don't know what a slope of 4 is here. There's no numbers on it. It does ask me to number the x-axis, so I'll do that in a moment. And then I want to go minus 3 for 1 second, and then I want to stop. Right. That was kind of probably a little bit longer than I needed to go off to the side, wasn't it? That'll do. You know, I'm going to fix that one more time. I'm going to use the grid lines from above to say that's 2 seconds, 3 seconds, 4, 5. Okay, that'll work for me. And now I'm going to number my axes the way it asks. All right, remember I'm moving at 4 meters per second for the first 2 seconds, so I will call this distance right here 4 meters. And I'll call this position right here 8 meters. Okay? And so I'm kind of asserting that this right here is 5 meters. And I'm definitely freehanding it. And you'll get a little slack on the test too, like this. I don't think this dotted line is necessary to number the axis. I'm just showing you that I went backwards 3. Right? Again, the way that I know I went backwards 3 is because of the graph above. The area under the graph here, this area right here is 8, and this little area right here went backward is minus 3 times 1 second, so it's minus 3. Okay, so 8 forward in 2 seconds, minus 3 in the next second. And that's what I'm getting those areas from. You don't have to know that even to do the problem, I don't think. But certainly, I think it's going to help to make it a little simpler. Let me move down to my writing lines up with the picture again. Good. I'm going to continue to number the x-axis as well. It only says to number the x-axis. I think it makes sense. We're going to number our x-axis because I want to make sure that I denote when 2 seconds is that it turns around and when 3 seconds is that it stops. Okay. All right. How far did it travel from 1 to 2? Again, I could have done this from the previous graph. I could also do it here. I could look at it right here at 1. And I could look at it right here at 2. And I could say 8 meters minus 4 meters equals 4 meters. It's the same answer I got up above. What is the total displacement? Explain your answer. Okay, I would say my total displacement would be I ended up at 5 meters. Okay, it's over here, remember? After going backward 3, we ended up at 5. We started out at 0 meters, so our total displacement is 5 meters. This little equation that I just wrote down below here, much like that. This little equation here that I wrote down below just comes from the idea of delta x. Okay, so x final minus x initial, that's all I'm doing to find that displacement, the change in the position. And that's what delta x equals. the triangle again in front of the x just being delta or change. Okay, let me go on to the next page. Got a little bit of a math problem here. So Johnny drives to Wisconsin, 1920 miles in 32 hours, returns home by the same route in the same amount of time. Determine the average speed. The average speed is pretty straightforward. We're just going to do distance over time. And we're not going to worry about direction or minus signs or any of that because we're doing speed. Okay? And so I will just say, well, he went 1,920 miles up to Wisconsin. And then he went 1,920 miles back home. Put in some units. We don't like naked numbers. And then that took 32 hours plus 32 more hours. So the total distance would be 3,840 miles. Do this in my head again, so forgive me if I make a math error. 64 hours. And I don't know offhand how many hours that is. It's 60. Maybe 60 miles per hour. Okay? If I did it right. If I did the math wrong, forgive me. Next one I want to know about velocity. Now this is a round trip. Okay? He returns home. And so the answer is that if you start here and you go over there to Wisconsin and then you go back home again, you end up right where you started. And so this, we actually care about direction, and we'd have to say that the change in the displacement would be 0. It'd be 1920 minus 1920, or just 0. He ended up right where he started. And I'd put this over 64 hours, and I would just get 0 in my average velocity. Compare the two values, explain a difference, and so I would say velocity is a vector. You don't have to use that word. We used it once in class. But more specifically, I would say velocity has direction. Okay. I might also say that velocity uses displacement. Remember, displacement is how far you end up from where you started in a straight line. Okay, and speed does not use displacement. Speed uses distance. Doesn't matter which way you're going, doesn't matter which path you take to get there, it's just the overall distance. All right. Let's go on to the next problem. Listen to the velocity versus time graph below. Looks like we're moving forward for the first 3 intervals of time. Whether they're seconds or not, I can't tell. Let me move backward, or a negative velocity, for the next 4 intervals of time. So it's asked to describe the behavior of the object. I kind of just did. I wouldn't even call these seconds necessarily unless you want to. If you call them seconds on a test, I would mark it wrong. I'm just going to say intervals of time, though, because I don't really know what the interval of time is. Also, I would want to say this one's 3 times faster. I was going to write forward with number 4. It's kind of silly. Forward, or a positive direction. For 3 intervals of time. Okay. At a speed of 3. I don't know 3 what, meters per second, miles per hour, I just don't know. It doesn't tell me on the y-axis, and that's fine. And then I would say backward, or a negative direction. For 4 seconds. Okay, at a speed of 1. Again, I don't know what units they are. Whoops. I didn't mean to do that. All right. And so again, this right here is positive velocity, 0 velocity, negative velocity. So here's where I got my -1 unit, and I counted upward 1, 2, 3 units for the positive. Okay. Next one says draw a motion map that represents the behavior of the object. Okay, we'll do that. So I don't know where I start. This velocity versus time graph doesn't tell you x initial. It just tells you the change in x. Okay, we don't know where we start with this. So I'm just going to choose to start right here. I'm going to say this is forward for me. And I'm going to draw these arrows of a certain length. I'm going to try and make them all about the same. And I'm going to do that for 1, 2, 3 arrows because I have 3 seconds to travel forward. Then I'm going to start here in the same position. I'm going to move backward. If I'm going to move backward very slowly, I want to make these next arrows 1/3 of the length of my previous arrow. See how I made 3 of them equal to the 1 previous? Because I'm moving backward at 1/3 of the speed. Okay? And that would be an acceptable motion map for this graph of motion here. All right, 4 little arrows going backwards for the 4 seconds going backward. Let's go on to the next question. Oops. The arrow. There we go. This looks like a little problem here. This is not the problem on your worksheet, though, is it? Let me find your worksheet last problem, and I'll be right back with you. Okay, so here we are looking at your last problem. We have 2 sprinters starting 100 meters apart, okay, and they run directly at each other, similar to what we did in class today with the 2 cars that had a head-on collision. One starts at the 0 meter mark when it goes to the constant speed of 7 meters per second. The other one starts at a 100 meter mark and runs toward the 0 with a speed of 13, almost twice as fast. Find the position where they meet and the time it takes them to reach their position, and then draw a motion map of them, labeling each runner as R1 and R2. I'm going to start with the motion map because it's going to help me understand what's going on here. So I'm going to draw, here is my 0 mark, and here's my 100 mark, and I will draw the slower person starting at 0 and moves at 7 meters per second. I'm not sure exactly how many seconds it will take, but I'll just draw some arrows here to start with. Okay, and I'm going to draw the other person with the color, and I'll make their arrows about twice as long because they're going this way, right? And they're moving about twice as fast. Hopefully, if it only takes about 4 or 5 seconds, they'll be able to meet in the middle and not look too conflicted. My arrows are not very uniform there. I might try that again. And let me actually see if I can select an arrow and just make more identical arrows. That way they all look just the same. How's that? Alright, so those will be my 13 meters per second backward toward the 0. Now let's go ahead and attack this problem. I would solve this as a system of 2 equations and 2 unknowns. And I would write down y equals mx plus b for each of them, just like we did with our 2 cars in class today. So I will say x, that's my position, okay, in meters, for the runner that starts at 0 is equal to 7 meters per second times time plus 0. My other equation I would work with is I would say x, position in meters, is going to equal minus 13 meters per second. The minus, again, is my velocity vector direction going negative. This is going the other way. If the red arrows go to the right and they're positive, then the blue arrows to the left are negative. And that's how the difference between speed and velocity. All right, we're going to multiply that times time, and our initial position is 100 meters for our second runner. And now I want to solve for position and time. Just like we did in class today, I already have solved for x equals 7 meters per second times 2. I can just put that into my second equation over here. I'll make a substitution. Instead of x, I put in 7 meters times t. Just plug it right in there, okay? And then we're going to now just solve the simple algebra equation. It's one equation, one unknown, because I've already made a substitution. So I have a minus 13t here, and I will add 13t to both sides. That will move the 13 meters per second t as a group over to the other side. 7 plus 13 is 20, so 20 meters per second times t equals 100 meters. Since the 20 meters per second is multiplied times t, the opposite operation is division. And obviously 100 divided by 20 is 5 seconds. So 5 seconds takes them to meet. That will give me the time that it asked for. It didn't give me the position that it asked for. We can find that pretty easily now. We know it takes 5 seconds for them to meet. This runner that's running at 7 meters per second, right, that's the velocity they're running at. And so in the first second, they are going to cover 7 meters. In the next second, they cover 7 more. In the next second, they cover 7 more. So if I look at my little motion map down here, try and kind of reason this out, that should be 7 meters, 7 meters, 7 meters, 7 meters, 7 meters, and that's 5 sevenths is 35. Should be 35 meters. I can also look at an equation like this, that velocity average or constant is equal to change in position over change in time. And if I plug in the numbers I know for this first runner, that 7 meters per second is equal to the position where they meet, and underneath it I put in 5 seconds. I can see that to isolate the delta x, I'm going to have to multiply both sides by 5 seconds. Okay, my units of seconds cancel out. 5 times 7 is 35, and I get 35 meters once again. I can do the same thing with the 13, though. Let me switch colors off and do blue this time. I'll try and find a little room off here in the corner. But if I just treat this 13 meters per second for 5 seconds, and I remember that I started out at 100 meters, right? So every second I'm getting 13 away from 100. So, I'm just going to do a little more room. Let's do this. And so I started off at 100 meters, and I went this way. So the first time, that will bring me back to a position of, this is 13 meters, now I'm at 87. And I can keep on going. I can count them up by hand, and I would find out that 13 plus 13 plus 13, and one more 13. That's going to give me 65 meters all told, as it should, because 100 minus 65 is 35. So that's the position where they meet. If I want to do that with an equation, I could say that the average or constant velocity of the second runner starts at 100 meters is their change in position over change in time. Again, change in position is final minus initial. You should remember that from chemistry from last year. If you had chemistry last year, that change in temp was always final temp minus initial temp. So I will put in their speed of 13 meters per second. I will set it equal to their final position. That's x final. I don't know that. Minus 100 meters. That's their x initial of this second person. And I will put all that over 5 seconds. All right. Let me erase a little bit of what's down below. Erase this right here. And then continue forward with the math. Yeah. So I would multiply both sides of the equation here by 5 seconds to cancel on top and bottom. This kind of gets the unknown x closer to being by itself. 5 seconds times 13 meters per second. Seconds on top and bottom cancel, and I get 65 meters equals x final minus 100 meters. Looks like I've dropped a negative sign here somewhere. Oh, there's a negative sign I dropped. I see it now. So I was about to get 165 for my answer. That would be really nice. Let's remember this velocity was a negative 13, which gives me a negative 65, which helps me not to have 165 for my answer, which would disagree with all the rest of the answers. So here I'll add in 100 meters to both sides of the equation, and this becomes 35 meters equals x final. So I show that a couple different ways. Easy one of the motion maps can show it. Also, I can use the velocity equations for either one of the runners, either the 7 meter per second or the 13 meter per second runner. They all are going to give me the same answer in the end. And there's more than one way to work these problems. And each one of these is different representations of showing what you know about the question. All right. So you have to know how to do all these things for the test. You have to be able to very quickly and easily work with position versus time graphs. You have to be able to work with velocity versus time graphs, knowing that the area underneath the curve is the displacement you've gone. And you should be able to draw one from the other. So if you have a velocity versus time, you should be able to draw position versus time. If you have a position versus time, you should be able to draw the velocity versus time. All right, they should be able to go back and forth. One more time, just to emphasize that, the slope of the position versus time graph, right here, this slope on this graph, let's say the slope is 4, okay? That means that on the graph above for velocity versus time, you actually graph a 4, okay? Because you're graphing the number on the y-axis, this nice constant horizontal line is from the slope down here. Okay, the slope of this is the velocity, and so the slope, 4 meters per second, becomes a horizontal line at the value of 4 on the velocity versus time graph. That's how you go from one to the other. And again, we did this in the lab. We've done this on some worksheets, and we saw this also when we had the two cars hitting each other on Tuesday in class. Hope this video has been helpful for you, and only 27 minutes. Have a great day, and good luck on your exam.